Hi guys, today we're going to be doing an experiment on phages. I know I haven't done that many videos on phage before, but I've been picking up a few new techniques. So today we're going to be doing a video about top agar, and that's going to allow us to titer our phage stocks. So I'm going to explain a little bit about the experiment we're going to do in this first video, and then I'm going to kind of show some of the stuff we're going to be using, and then after that we're going to go into the actual protocol. So I've done a little bit of setup. I have a bunch of plates that I've already marked up. We'll go over what all these markings mean. I have a few PCR strips right here. We're going to be using these for serial dilutions later. I have some overnight culture with saturated, that we have E. coli, different strains with different plasmids that have grown overnight to saturation. I have my flame. I just want to keep everything sterile here, and I want to use it whenever I'm doing sterile technique. And I have obviously my pipettes, and we're going to be using a multi-channel. I think I've gone over how to do serial dilutions on E. coli before. We're going to eventually be doing something very similar but with phage this time. So the experiment we're going to be doing today, again, is we're going to be titering phages. So I mentioned earlier, a few seconds ago, that we have different strains of E. coli. So we have different E. coli lines. We have DH5 alpha, DH10B, MG1655, and MC1061. And in these four different strains, I put in two different plasmids. This set of four has a plasmid that has an inducible IM gene. The IM gene is a protein from phage T4 that is a periplasmic protease. So what happens is when the T4 phage infects your E. coli, it shoots its DNA in, it runs its programming. Part of that programming is it makes this protease that goes out into the E. coli periplasm, and then it will prevent infection by more phages. So this is super infection protection, because once that phage gets in there, it wants to dominate everything. It doesn't want any other phages coming in messing up its party. So the idea behind this is if we put this IM gene, this T4 IM gene, in these four strains of E. coli, then we subject that E. coli to T4. Hopefully, if that IM gene is there, these E. coli should live. That's the idea. And to test this, what I'm going to be doing is I'm going to be, since I said this is under an inducible plasmid, I'm going to be putting these E. coli on these plates, like an even spread, and then I'm going to be making a serial dilution of my T4. So that means in our T4 lysate we have something like 10 to the 9th different particles of T4. And then we're going to do a 10-fold serial dilution, and hopefully we'll see that when we have induced the expression of our IM gene, that we get a slight protection. That means that we have phage clearing to a lower level. But when I do not induce, that there's no protection and the phage will kill every single one of those bacteria, which means that our serial dilution will go out a lot farther. So at the end of this video, we'll see what that looks like. I know this might sound a little bit confusing right now, and I'm probably not doing a great job of explaining it, but you will hopefully see it. So again, just one more time, I'm going to try to say that to really drive it home. We have our E. coli. Inside of our E. coli, we have an inducibly expressed IM gene from T4. It's under the PBAD promoter. That means when we add arabinose, we will get this IM protein from the T4. And if we don't add arabinose, we will not get that IM gene. So we're going to spread our E. coli plus or minus arabinose, and then add phage. And we're hoping to see that minus arabinose, T4 kills a lot of cells, plus arabinose, we get that IM gene, we don't see that. So that's kind of the core of the experiment. So in that exact same vein, we have another phage protein called C1. This is a lot more common. We have the lambda C1. Lambda is a very, very common model phage system. It's been around for years. It's very well studied. And C1 is also a protein that will protect from superinfection. It's a different mechanism. Whereas the IM gene from T4 is a protease and will chew stuff up. Actually, I can't remember if it's a protease or a nuclease. I think it's a protease. I think it does something in the periplasm. It either prevents the DNA from going in or it chews it up as it's being injected. I'm sorry, I can't remember. But the C1 is actually a transcriptional repressor. So C1 is a constitutive dimer. So it will come together. and then it will sit down on the lambda DNA, and then it will repress the transcription from the PR promoter, and there's a decision circuit inside of the lambda phage, which I'm not going to go into because it's really complex, that decides between lysogeny and lysis. So lysogeny means the genome incorporates itself into the DNA of the E. coli. The phage genome incorporates the lysis-lysogeny decision means that the lambda phage has to decide whether it will incorporate its own genome into the E. coli genome, or whether it will just go lytic and make more of itself. So when we have C1, it goes into lysogeny. So hopefully what we're going to see here is when we have our C1 and we add lambda phage, our cells will live. So in this experiment we've actually modified our C1 a little bit so that it has a different dimerization domain on it, and it is going to only dimerize if we supply another molecule. So I have these two different strains of E. coli, and again that C1 is in all four of those strains I mentioned earlier, and we're going to put all of them on these plates using top agar, and then we are going to do a serodilution of different phages and see whether the T4 IM gene will protect against T4, whether the C1 TRA-R that we've made will protect against the lambda phage. And then the point of this experiment is we're actually also going to want to see whether T4 will protect against lambda, which it should not, and whether the C1 lambda will protect against T4. So we're checking for orthogonality here. So hopefully that made sense. If it didn't, you can post comments and I will try to answer them to the best of my ability. And if also, you know, don't worry about too much about the experimental design. If you're only interested in the wet techniques, that's totally cool too. This is just a little bit of extra. But we're going to be going in how to do top agar and how to do titers on phage. That's probably the more important practical thing. I'll probably put a note in the beginning of this video warning people that this is just extra and it's not necessary to understand how to do this technique. It's a pretty common phage wet lab technique. So thanks for watching. We'll be back in a couple of seconds and we'll start actually doing the top agar.